This lesson is for Advanced Algebra, Lesson 9.5 on common logs. Common logarithms are logs that have a base of 10. Why do we need to know about logs? We need them in order to be able to solve equations when the exponent is missing. Earlier in the chapter, I had students solve a problem that they had to use trial and error to solve. And trial and error is not a great method for solving in algebra. We usually want to have a method where we do things to both sides of the equation. So logs are going to help us when the exponent is the missing piece. So what is a log or a logarithm? Well, it's going to look like log, L-O-G, of a number equaling another number. When you have a problem that says log like that, it's in logarithmic form. Most students are going to be comfortable or more comfortable putting that log problem into exponential form. All log problems have a base, and it's usually written down here as a subscript. If there is no subscript written or no base given, it is assumed that the base is the number 10. The answer to a log problem is always going to be the exponent part. So in this case, the y represents the exponent. So if we take base 10 and raise it to the y, we'll get the value of x. So let's practice that now with just a basic log problem, log of 100. It's a base 10. We don't know the answer, so I'm going to fill that in with a question mark. You could also fill it in with any other variable. If I rewrite it in exponential form, it's base 10. I don't know what I'm raising it to, but I know that I'm going to try to get to the number 100. So common logarithms, the type that we're doing today, have a base 10, and those are easy to work with. That's why they're called common. So when you're working with powers of 10, you basically just look at how many zeros there are. So if we're trying to get from 10 to 100, we're trying to get to a situation with 2 zeros. And we know that 10 squared equals 100, so 2 is the answer that we're looking for. So what's neat about log problems is that since the answer to every log problem is an exponent, what that does is it allows that exponent to become a regular number rather than how we're used to seeing it as a little subscript number or superscript number. So it turns that y number into a regular number, not an exponent. So let's try another one. If we're doing log of 1,000, remember that it's a base 10. We don't know the power. So if we turn it into an exponential situation, 10 to the what is 1,000, we're just counting how many zeros again. 10 to the 3 is 1,000, so the answer there that we're looking for is the number 3. Gets a little bit trickier when we do problems that are decimals. Again, fill in the missing base, fill in the missing answer. If you turn it into exponential form, we get base 10 to the what is 0.1. What I'd like students to try to do when they have a decimal is try to say the decimal correctly, meaning the way that you were taught to say it properly when you first learned decimals back in elementary school. So most of you probably weren't allowed to say 0.1 here, although that is fine. Most of you probably learned that that's the same as saying a tenth. And a tenth is the same as doing 1 over 10. So these two expressions are equivalent to each other. And so now we can figure out what the exponent is that gets us from 10 to 1 over 10. If you think back to what we did in chapter 7 and 8 with exponents, when the base flips over, that means we used a negative exponent to get there. Since the 10 is not changing in value at all, we're not raising it to anything other than the power of 1. So the exponent here needs to be a negative 1. Which leads me to another statement that I'd like students to memorize. In addition to the answer to a log problem is an exponent, you should definitely memorize that logs of decimals are negative. So let's try one more here. If we put in the missing base and the missing exponent and turn it into exponential form, we say 10 to the what is 0.01. Another way to say that is 10 to the what equals 1/100th, which is the same thing as saying 0.01. So since that is 1/100th, which is the same as 1 over 100, I know that I need a negative here because the 10 has moved to the bottom of the fraction. And then because I'm turning 10 into a 100, I know I need a power of 2 because 10 squared is 100. So I know my answer is going to be -2. Some other types of questions that students need to be comfortable doing are problems like number 5. I call them log property problems because there's really kind of a pattern here that you'll start to see. When you rewrite this one in exponential form, you have your base 10. We don't know what the power is, but we know that we're trying to get to 10 to the 4. Well, the exponent's kind of staring us in the face. The power that we're trying to get to is the power that they already gave us. It's kind of the same as them asking us to do the log of 10,000. If we just counted the zeros, another way to write that would be 10 to the 4. So the 4 is the answer that we're looking for. Remember that the answer to a log problem is an exponent. So if they give us the exponent, we're ready to go, and we don't even need to rewrite it in exponential form. A trickier one is one like number 6 here. If we fill in the missing base and the missing exponent and rewrite it, we get 10 to the what is the 5th root of 10. Remember that log problems are really just exponent problems rearranged. So if I try to rewrite this using an exponent, taking the 5th root is the same as raising to the 1/5 power. So now, what is the exponent that we're looking for? There it is, it's the 1/5. So those tend to be ones that students get stuck on because they can't see that there's an exponent there. So if you're working with a root, try to write it in exponent form, and that'll be what you're looking for. The last one is log of -10. If you try to figure out 10 to the what is -10, you're going to be there a while. You can't raise 10 to a power and turn it into a negative number. Regardless of whether or not you put in a positive or a negative exponent, you're always going to get a positive result. The only way to get a negative result when you have an exponent is if the base were negative to begin with, and logs are never going to have negative bases. So, another phrase to memorize, you can't take the log of a negative number. So all we're going to say here is no solution. So we've talked about why we use logs and what they are. Now let's look at how we use them. We use them to solve problems. If you're given an answer or a question like log of x equals 3.5, again, use your knowledge of logs to rewrite it in exponential form. It's a base 10. Even when there's no base listed, we can assume that. The 3.5 is the answer, so that's the exponent, and we're trying to get to x. So now all students would need to do here is use your graphing calculator and type that in, 10 to the 3.5 power. And when you do that, you get about 3,162 for x. Similarly, on number 9, first we're going to use a little bit of algebra to isolate the things that are near the x. The log is right next to it, but the 5 is further away. So we're going to get rid of that 5 by dividing. If I divide by 5, it's going to cancel on that side, leaving me log of x is 9/5. I could go ahead and get a decimal for that number if I wished, or you could just leave it, because we know that in the next step we're going to rewrite it in exponential form. It's a base 10 problem because there's no base listed. The 9/5 is the power, and I'm trying to get to x. Again, this would be a graphing calculator portion where you would literally type in 10 to the 9/5 power. When you do that, you get about 63 for x. Another type of problem you might run into is one like book example 3 from page 610. They ask you to find two consecutive integers, integers meaning in a row or right next to each other, that works with log of 5673. So we want 5673 to be in between the numbers that we're working with. We're not going to be able to answer it exactly, but we're going to be able to get a range of numbers. That's why they want us to give two answers. So I'm going to start with just regular old powers of 10. I know that 10 squared is 100, and 10 cubed is 1,000. So far I'm getting closer and closer to 5673. So let's go to the next one, 10 to the 4. That is 10,000. And whoa, 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 now we're too big. But isn't that number in between those two? So, in between which two consecutive integers is the log of 5673? It's in between 3 and 4. So when you're doing a question like this, if they ask you for two consecutive integers, you're just going to use powers over and over and over again, and you're going to find which two surround the one that you're working with. The last thing we're going to just look at or mention here is a little bit about graphing. When you graph a log problem, it's basically the reflection image of an exponential curve. The name is not very original here. The name of a log graph is simply a logarithmic curve. Notice that it resembles an exponential curve, but it points the other direction. Goes from low to high in quadrants 1 and 4. Notice that the line does not cross the y-axis, so the y-axis is an asymptote. Remember that the exponential curve had an asymptote as well, but that was on the x-axis. So now the y-axis is the asymptote. Another way to describe the y-axis is simply to say x equals 0. And so the last thing we need to mention here, since we've covered why, what, and how, the last thing is if. What if the base isn't 10? Since all the problems we did today were base 10s because they were common log problems, not all bases, when you raise to powers, are going to be base 10. So there are other kinds of logs that will be coming up in future lessons.